Okay, let's dive right into this explainer and completely demystify one of the most brilliant, historically intimidating cheat codes in all of physics. If you've ever looked at a textbook on electricity and magnetism, you've probably seen a ton of complex integral equations that look, quite frankly, like an alien language. But today, we're going to bypass all that heavy calculus and just focus on the beautiful, intuitive logic underneath the whole thing. We are talking about Gauss's law and electric flux. Now, before we get completely bogged down in the math or the formulas, I really want you to think about this puzzle. Electric fields are entirely invisible, right? We can't touch them, we can't snap a picture of them directly, yet they govern almost everything in our modern world. So how in the world do you measure something you literally can't see? Keep this question in the back of your mind, because throughout this explainer, we're going to build a magical, imaginary 3D scanning box to solve it. Here is our step-by-step roadmap for cracking this code. 1. Catching the invisible wind. 2. The area vector explained. 3. Calculating electric flux. 4. Enter Gauss's law. And finally, 5. Applying Gauss to real shapes. Part 1. Catching the invisible wind. To really understand electric fields, we first have to ground ourselves in something tangible. So the absolute crucial point here is that flux is really just a fancy scientific word for flow. Seriously, that's it. In physics, when we say flux, we just mean the volume flow rate, how much stuff is passing through a specific window in a given amount of time. Whether that stuff is water rushing through a pipe, air blowing through an open doorway, or invisible electric field lines, the fundamental concept of flux remains exactly the same. And this comparison brilliantly illustrates our starting point. Think about a simple physical scenario, an airstream blowing through a square loop. You intuitively know that the amount of air you catch depends on how big the loop is and exactly how you angle it into the wind. Well, we apply that exact same logic to our physics problem. Just as you can measure an airstream blowing through a physical window, you can measure invisible electric field lines piercing an imaginary boundary, which we call a Gaussian surface. Moving on to part 2, the area vector explained. So we know what the flow is, but how do we mathematically describe the surface it's flowing through? You'll probably run into this super formal textbook definition. An area vector is a vector whose magnitude is equal to an area and whose direction is normal to the plane. Okay, don't let that intimidate you. In physics, normal literally just means perpendicular. Let's look at what normal to the plane actually looks like in reality, because visualizing it makes it incredibly simple.
Looking at this flat square patch, that blue arrow, the area vector, is essentially like a needle poking straight out of the surface at a perfect 90-degree angle. By attaching this normal vector to our surface, we've basically given a flat window a clear mathematical direction. And this is absolutely vital, because the amount of flex we capture depends entirely on how the incoming flow aligns with this exact needle.
Part 3, calculating electric flux. Now that our surface has a defined direction, we're ready to see how the electric field interacts with it to actually create flux. It's time to set the rules of the game. When calculating flux through a closed surface, there are exactly 3 absolute rules you need to remember, and they are beautifully simple. If the field lines pierce inward entering the surface, that's negative flux. If they pierce outward exiting the surface, positive flux. And if the field lines just sort of skim along the surface without actually crossing the boundary, that is exactly zero flux. Now check out how we can spot those 3 rules mapped onto this random, kind of weirdly shaped 3D potato. We've got this imaginary Gaussian surface sitting right in a uniform electric field. Look at patch 1. The area vector points out, but the electric field points in. It pierces inward, so the flux there is negative. Over on patch 3, the field pierces outward, so that flux is positive. And right there at patch 2, the field just skims right across the top of it. It doesn't pierce the skin of our potato at all, meaning the flux there is a perfect 0. Let's test this logic together. Imagine wrapping our Gaussian surface not as a potato, but as a rigid cube immersed in a uniform electric field traveling straight along the z-axis. Looking at this setup, the field enters the rear face. That's piercing inward, so the flux there is negative. The field exits at the front face. That's piercing outward, making it positive. And the top face, the bottom face, the sides, the field lines are just skimming perfectly parallel to them. Because literally nothing is entering or exiting those specific faces, their flux is exactly 0. Which brings us to part 4, enter Gauss's law. This is the main event, everyone. This is the exact moment we transform our basic understanding of flux into the ultimate physics shortcut. Gauss's law simply states that the total electric flux through any closed surface is directly proportional to the net electric charge hidden inside that surface. This means our imaginary boundary acts as a high-tech 3D scanner. By just sitting on the outside and counting the net number of field lines piercing our imaginary box, we instantly know the exact magnitude and sign of the charge hidden inside. And we don't even have to open the box to look. The true beauty of this law is the stark difference between wrapping our imaginary surface around an actual charge versus wrapping it around completely empty space. If there is a net charge inside your surface is going to have a net positive or negative flux, meaning more lines leaving than entering, or vice versa. But if you enclose empty space, any field line that enters one side of your box must eventually exit the other side. The negative flux perfectly cancels out the positive flux, leaving you with a net flux of 0. Let's see a prime example of the scanner in action. Imagine a spherical Gaussian surface just like this one. We don't initially know what's in the center, but observe the field lines. Every single one of them is pointing straight inward, piercing the boundary from the outside in. Because our rules strictly dictate that inward piercing field lines equal negative flux, we know immediately and with absolute certainty that the enclosed particle must be a negative charge. And finally, part 5, applying Gauss to real shapes. Let's wrap up this explainer by putting all these tools together for the grand finale. Let's see what happens when we throw multiple charges into the mix. Here we have a dipole, a positive and a negative charge right next to each other. We've drawn several arbitrary, blobby Gaussian surfaces around them. Notice surface S1 up top. The electric field is outward for all points on this surface. Because it only has outward piercing lines, it confirms a net positive charge inside. Conversely, look at surface S2 down below. It has entirely inward piercing lines, creating negative flux, which perfectly confirms a net negative charge is trapped inside that specific boundary. But look really closely at surfaces S3 and S4. This brilliantly illustrates our empty space rule. S3 is drawn right in the middle of the field, but it actually encloses no charge whatsoever. Every field line that enters at the top leaves at the bottom, so the net flux is 0. Now look at S4, that massive oval enclosing the whole system. It encloses charges, sure, but it encloses equal positive and negative charges, so the net enclosed charge is 0. Gauss's law requires the net flux to be 0, and visually, it makes perfect sense. There are exactly as many field lines leaving surface S4 as there are entering it. So now that you've got a solid handle on the brilliant intuitive logic of Gauss's law, you literally hold the ultimate cheat code for electromagnetism. We only used simple shapes today, but just imagine the incredibly complex, real-world force fields you could decode with us. By cleverly choosing the shape of your imaginary scanner, like a cylinder for a long wire or a flat pillbox for a massive sheet of charge, you can solve literally impossible calculus problems in a matter of seconds. How might you draw a surface to measure the field inside a solid sphere of charge? Well, I'll leave you to ponder that puzzle. Keep questioning, keep visualizing, and thanks so much for exploring this with me.